Hi, my name is Neely Dupuganti and I will be presenting the fourth lab we performed for Physics 2212, which covered circuits and capacitors. To introduce this lab, circuits are powered by an electromotive force, and a closed loop allows current to flow. The purpose of this lab was to measure and study the electric interactions in circuits and capacitors and compare their results to our expected calculated values. We studied series and parallel resistors in circuits and their effect on voltage and current through the use of multimeters. Lastly, we studied how capacitors charge and discharge and their interactions with light bulb resistors to measure time-dependent voltage in an RC circuit. In part 1, the ammeter read 0.02 amperes as predicted, and the voltmeter measured 3 volts. In part 2, the light bulb initially glowed bright and then dimmed as the capacitor charged. The charging time was directly related to the amount of resistance. In part 3, the RC time constant was calculated to be 6. In this presentation, I will cover the fundamental principles, all the parts of this lab, and the additional questions with a conclusion. The first fundamental principle for this lab is Kirchhoff's loop rule, which states that the sum of the voltage differences across a circuit must equal 0, which is energy conservation. Next, the node rule deals with charge conservation and states that the incoming current must be equal to the outgoing current. Finally, capacitors are devices that store electrical charge. They are initially uncharged and offer no resistance, but after time, they become fully charged and offer much resistance. In part 1 of this lab, we studied charge and energy conservation in series circuits. The circuit consisted of two 1.5 volt batteries, a 47 ohm and 100 ohm resistor in series, and two ammeters placed before and after the resistors. For the results, the ammeter read 0.02 amperes as predicted, and when reversed it read negative 0.02 amperes. When the voltmeter was replaced with the first ammeter, it read 3 volts. Throughout the circuit in part 1, potential differences were measured at different segments, as can be seen in the table correlated with the first picture. If you add all these potential differences, the sum equals 0, which represents Kirchhoff's loop rule. The bottom image shows a graphical image of how potential differences vary with segments of the circuit. Furthermore, an ammeter is placed parallel with a 100 ohm resistor, as can be seen in the left image. In this setup, the ammeters both read 0.06 amperes due to the node rule. Resistances were calculated for the resistors, wire, and ammeter. For the resistors, our calculated experimental values vary just slightly from the actual ohmic resistor values, as can be seen. Also, the wire and ammeter had no resistance as expected, given there is no potential drop in these segments. In part 2 of this lab, we evaluated an RC circuit, which included a 10 ohm light bulb and a 20 ohm light bulb, a 9 volt battery, and a 200 microfarad capacitor. When the battery, capacitor, and ohmic bulb are connected in series, the light glows bright and then dims as the capacitor continues to charge and gain resistance. This is evident in the loop video to the right, displaying a charging capacitor. When the circuit is disconnected from the battery, the capacitor discharges, causing the bulb to brighten and then dim again. The charging times and discharging times were measured for each ohmic light bulb. For the 10 ohm bulb, the charging and discharging time was around 10 seconds, while for the 20 ohm bulb, the time was around 20 seconds. These results showed that the capacitor charging and discharging time are directly proportional to the amount of resistance. In part 3 of this lab, I measured the time-dependent voltage across a discharging capacitor. The video to the right shows a visual representation of how a capacitor discharges. Notice that the light bulb glows bright and then dims as the capacitor loses charge. A linear representation displaying the significance can be modeled through the below equation, where RC is the time constant, representing the time the voltage drops to 1 over E of the original value. The setup of the circuit included a 9 volt battery, a 200 microfarad capacitor, and a 30 ohmic bulb, and the goal was to calculate RC using potential difference values at different time increments. The results of this part of the lab can be seen here. In the data table to the left, 20 different values of the potential difference can be viewed for each 1 second increment. When the natural log of the potential difference at each time segment over the initial potential difference is plotted versus time, a linear line is constructed with a slope of negative 0.1666, which can be used to calculate the RC time constant. The RC value is calculated to be 6.00, which matches the expected value. To conclude, if we were to do this lab in real life and use an actual ammeter instead of an ideal one, there would actually be resistance due to the ammeter, and as a result, the current readings on a real ammeter would be smaller. If we used a real battery to charge a real capacitor with no resistor in the circuit, the real capacitor would take slightly longer to charge because real batteries and circuit components have internal resistance. Lastly, through this lab, our conceptual knowledge of circuits, resistors, and capacitors was experimentally validated in all parts.